Okay, here we go. Number 2. The number of mosquitoes in a field after a major rainfall is modeled by the function m, defined this way. T is the number of days after the rainfall ended, and we're dealing with time intervals from 0 to 18. So only the first 18 days after the rainfall. And those units are going to be very important as we get into part A, which of course says, using correct units, interpret the meaning of the derivative of 15. The derivative of m at 15 equals negative 171. I've already given away part of the answer in the way I reworded the way the problem was. And it said put it in the context of the problem. So let's just do this. Part A. The derivative at 15 equals negative 171 means, it means what? Okay, well, the derivative is a rate of change. Rate of change of what? Mosquitoes over time, and time is measured in days because they said so, means that at t equals 15 days, the number of mosquitoes in the field is, okay, changing, yes, but I'm going to get a little more specific with my language, and if you don't word it exactly like this, that's okay. I do want to warn you not to overuse your negative, okay? I'm going to say is decreasing. I'll tell you what I mean by don't overuse your negative in a second. Decreasing at a rate of 171 what? Okay, we need units. They said so. 171 mosquitoes. It's a rate of change, so you better have the word per in there. Per day. Okay, here's what I mean by don't overuse your negative. I already told you that the rate of change, or the number of mosquitoes, is decreasing, and therefore I don't need to say the number of mosquitoes in the field is decreasing at a rate of negative. Don't do that. You've just double negative this thing. So it is decreasing at a rate of 171 mosquitoes per day. You could say it is changing at a rate of negative 171 mosquitoes per day. That's also good too. So just a couple things to notice. You do need units, mosquitoes and days. You need to explain what the 15 means. Like what's the 15 there for? I don't know. Well, it means that's the time. So also we need to make sure that we're dealing with a rate. Okay, there's part A. That was pretty straightforward. But then part B asks us something that's a little more complicated, and it has to do with the extreme value theorem. Let me pause right here and talk about the extreme value theorem. And let me show you a trigger word too. Not trigger like, like triggered, but trigger like, oh, that reminds me of the extreme value theorem. So the absolute maximum number of mosquitoes, I need to do something with my derivative. Like I'm going to need to set my derivative equal to 0, but I also need to consider the endpoints of an interval. Maximums and minimums occur, I've said this a lot, at the endpoints of an interval, or where your derivative equals 0, or where your derivative doesn't exist. This derivative is going to exist anywhere, but that's not relevant at the moment. So let's actually just go ahead and start by finding the derivative. So the derivative of number of mosquitoes will be negative 3t squared plus 24t plus 144. This is calculator inactive, so we're going to have to factor this thing by hand. It's not going to kill us. We'll be okay. And we will set this equal to 0 in just a moment, but we're trying to find critical numbers, basically, numbers where we have potential maximums and minimums. So let's factor a negative 3 out. That's going to help us a lot. We'll have t squared minus 8t, and then 144 divided by 3 is, I'm going to brain fart right here, that would be 48. Yeah, so minus 48. Okay, and then we'll have negative 3, and then, let's see, t minus 12 and t plus 4, and that's going to be equal to 0. And so now we will set our factors equal to 0, and we solve. You've seen this process many times before. T is 12, t is equal to negative 4. Okay, well, let's dabble in reality for a second. We're dealing with the number of mosquitoes on the day t. Well, we're not going to have t equals negative 4. Well, you can't move backward in time. Within this context, actually, you could. That would be 4 days before the rainfall ended. But they told you the interval is from 0 to 18. So it's outside our interval anyway. So we don't have time-traveling mosquitoes. But we do have a negative time value that's not even in the interval we're dealing with. So 12 is really the only number we need to deal with. And so we're going to do what we call sign analysis. And we'll put our number line down. Don't go from negative infinity to infinity. Don't. We're going to go from 0 to 18. and put a 12 in somewhere in the appropriate place there. Doesn't have to be exactly scaled correctly. And I want to plug in numbers from this interval and from this interval into the derivative and figure out the sign of the derivative to determine if it's positive or negative. Let me rephrase that. I shouldn't use the word it. To determine if the derivative is positive or negative, and therefore I'll know if my function's increasing or decreasing. I'll know if I have a maximum or a minimum, all that fun stuff. So I'm going to just pick a number from 0 to 12. I think 1 is a really obvious candidate. And if you plug it into the original derivative before you factored, you can work out an answer. It's great. I personally really like to go into the factored form, including this -3 that we factored out. You better include that because it's negative. It's going to tinker with your signs if you're not careful. So if I plugged a -1 here, I don't care what the number is. I just care about the sign. -1 goes here. I'm sorry, +1 goes here. Sorry. +1 goes here, I have a positive. +1 goes here, I have a negative times a negative. So negative times negative times positive. My derivative on this interval is positive. Okay, so let's just kind of think ahead a little bit and think about where this is going. If this interval is negative, I'll go ahead and tell you it is, but if this interval was negative, then at t equals 12, we have a maximum. That's it. We do, because the derivative is positive than negative, meaning the function is increasing than decreasing. So let's figure out if this is less or greater. I've already told you what it is, but let's just do it like for real. Plug in a 13. 13 goes here, you get a positive. 13 goes here, you get a positive. Negative times positive is indeed negative. 12 is a maximum. It is the only maximum we have. Okay. I have seen similar problems where you had more than one number in the interval that you had to contend with, and in doing so, you had to test the endpoints of the interval as well. So you don't have to in this case. So at the beginning of part B, I said, oh, it's extreme value theorem. Let's test the endpoints of the interval, and where the derivative equals 0, we actually just ruled out the endpoints of the interval. We don't need to deal with them. And the reason why is because my function increases, then decreases. This is the only maximum I could have. If I kept going for some reason, like if this went to, I don't know, 24, I'm making that up, but if it went to 24 and turned around at 18 and went up, it doesn't, but if it did, if 18 was one of our critical numbers here, and it went back up, I'd have to test all the way to 24. I would have to check the 24 because my function would be going up, down, then back up again. That's not the case. 12 is my only critical number. So let's read the problem carefully, and we'll go from there. Based on the model, what is the absolute maximum number of mosquitoes in the field? The answer is not 12. Okay, they're not asking at what time, they're asking number of mosquitoes. There's a huge difference. So let's find out how many mosquitoes there are. And then it also says justify your answer, which we'll put it all into words once we're finished. So I need to know the number of mosquitoes at 12. And this is calculator inactive, so haha, good luck with that. Negative 12 cubed, kind of thing you know off the top of your head, plus 12 times 12 squared. Actually, things are about to work out quite nicely for you. Plus 144 times 12. All right, I really hope you notice what's happening here. This is 12 to the third, this is 12 to the third, and this is 12 to the third, and one of them is negative, so basically you can just cancel them out. So that one's going to cancel with that one, and all you're left with is 144 times 12, and just for the sake of finishing this, 728 mosquitoes. Mosquitoes. Okay, so now let's put a justification for this on paper. It says justify your answer, and I am about to do so right now using all the work that we've already shown. So we're going to get some points for what we've already identified. You're going to get points for finding the derivative. I'm actually looking at the answer key right now to see how it's scored. So you'd get a point for this. You'd get a point for setting the derivative equal to 0. You'd get a point for identifying 12 as a candidate, and we've got 3 out of the 4 points we could get on this. We just have one more to get, and we're going to get it with a justification. The number of points and what they're looking for changes from problem to problem. I'm just giving you the specifics on this. So let's actually answer it in context and provide our justification. So here it goes. Let's start by talking about how we got the number 12. So, because the derivative of the number of mosquitoes changes from positive to negative at t equals 12, then the number of mosquitoes, M of t, has a maximum. I want to call it a relative maximum because it's, relative within its own position. It may not be the highest number of mosquitoes that ever existed in this entire thing. It actually is within this domain, but, whatever. Has a relative maximum at t equals 12. Okay, so we've just explained why we think t equals 12 is a really good candidate, and we're going to try it. Now, again, I would love to test the endpoints of this interval, but it's not necessary. And I think, again, it's obvious because the function, the derivative increases, the derivative is positive than negative, let me word it like that. And therefore, this is the only highest point you're going to have, only relative maximum. Let me word it that way, that's better. And let's just keep going with that. So because t equals 12 is the only, how do I turn this into the word only? There we go. Only critical point of m on the interval from 0 to 18. Because it's the only critical point, oh, that's an ugly font on only, from 0 to 18, that is the location of a relative max it is the location of the absolute max. Okay, let's put this into different words. We'll leave what we have on paper, but I want to explain what I'm saying. Again, we identified that 12 is a candidate, and then we said, oh, it's the only critical point, and so because it's the only critical point of relative max, like it could be the highest point, but it's the only potential highest point, so therefore it is the absolute highest point. And so, final answer, the maximum number of mosquitoes in the field. If you leave out a phrase like in the field, I don't think it's a huge deal, unless the problem is within different contexts, like there's a field and there's a forest, and you need to tell like which one's which, so you need to really be clear in that context, but this is the only location we're dealing with. The maximum number of mosquitoes in the field over the time interval. This is not the only way to word this. From 0 to 18 is 1,728 mosquitoes. That's a lot of mosquitoes. Okay, let's move on to part C, and we need to read part C very carefully. Very carefully. Here it goes. Excuse me. For what values of t, so our answer is going to be plural, right? We're going to have more than one value of t. Is the rate of change of the number of mosquitoes in the field increasing? All right, let's read it very carefully. The rate of change is increasing. All right, if my rate of change, my derivative, is increasing, then I'm dealing with the derivative of the derivative. And let me say it one more time. At what values of t, it's probably going to be an interval, is the rate going up. I want my rate to be increasing. Therefore, we need the second derivative. So just because I don't want to pull the other paper out and slide back and forth, I'm going to go ahead and rewrite the first derivative. Not necessary within the context of this problem, but I'm going to do it just so I can point at it. There we go. And now we need the second derivative, which should be pretty straightforward, negative 6t plus 24. And I think you know the very next thing you're going to write. You want to know where this function, where this second derivative is positive, because you want to know where the rate of change is increasing. You're looking for concave up, is what you're really looking for. We'll set this equal to 0, so we'll solve it, and t equals 4. Okay, that's great. We're done? No, we're not done. We're not done at all, because it says for what values of t is the rate of change increasing. It is at t equals 4 that the number of mosquitoes stops increasing at an increasing rate and begins to increase at a decreasing rate, or the other way around. Stops decreasing. Anyway, I'd say it wrong if I tried to say it again. But I'm going to figure out what interval we're talking about from 0 to 18. So this is where the second derivative equals 0. We need to know where the second derivative is positive because, well, the derivative is increasing. So we'll plug things into the second derivative. This should be pretty straightforward. From 0 to 4, if I plugged in like a 1, I would have a positive. So my second derivative would be positive. If I plugged in a 5, I would have a negative. There we go. Second derivative would be negative. So the answer to the question is from 0 to 4. I'm going to write it as a sentence just so I can make sure I put this thing in the context that I need to put it in. Make sure I'm really answering the question correctly as well. So it asks, one more time, for what values of t is the rate of change of the number of mosquitoes of the field increasing? So the rate of change, I'm going to leave off of the number of mosquitoes in the field. I'm going to leave that off. Is increasing for the t values from 0 to 4. 0 to 4. Okay, now we can argue about what happens at 0, what happens at 4. Technically at 4, it's neither increasing at an increasing rate or increasing at a decreasing rate, but the answer key actually has equal signs there because at that specific point, it's not that big a deal. You know, at t equals 4, we could argue one way or the other. Not a huge deal. Equal signs or not. Okay, last one. What eats mosquitoes? Bats. For t from 0 to 18, the number of bats in the field is modeled by this differentiable function b. Oh, we can take a derivative. That's going to come in handy. Where b is a function of the number of mosquitoes in the field. Okay, whoa, what? Now we have bats, and the number of bats depends on the number of mosquitoes, which really makes sense. You know, more mosquitoes, more bats. There's more to feast on. Based on the models, what models? Okay, this equation right here is an equation that models the number of mosquitoes. So based on that, write an expression for the rate of change. They're asking for a derivative, the number of bats at time t equals a. Well, what's a? Who knows? Just plug in an a. We'll get to the end of this thing and plug in an a, all right? So I need a function for bats where the number of bats is going to be determined by the number of mosquitoes. First time I read this, I thought, I don't have enough information. It's okay. I don't have to have enough information to get an actual equation where it's like, oh, 3 minus the number of the... No. The number of bats is a function of the number of mosquitoes, which is a function of time. It's a composite function. So as time goes on, the number of mosquitoes changes. As the number of mosquitoes changes, the number of bats changes. There you go. You have a composite function. It's really that simple. So let's read the problem again. I don't make it harder than it is. I was stretching for way too much information. I was like, they didn't tell me enough. They told you all you needed to know. They ask for an expression for the rate of change. Oh, okay, well, we'll take a derivative. That's the chain rule. So b prime of m of t times m prime of t. And they want this to be at time t equals a. Okay, great. So how about we plug in an a? Actually, yes, let's plug in an a, but let's go a little bit further. B prime of, all right, m of t was the number of mosquitoes, the function that represents the number of mosquitoes. So I'm going to jump back to this for a second. This step might seem a little bit unnecessary. I won't do it anyway. Put a dot there. And then m prime was negative 3 t squared plus 24t plus 144. And they want to know an expression for the rate of change of the number of bats in the field at time t equals a. This is correct, but let's plug in an a. You could have jumped straight to the very next step, and we would have been done. Negative a cubed plus 12a squared plus 144a times negative 3a squared plus 24a plus 144. Let us make sure we have fully answered the question. I do believe we have. And they only wanted an expression that represents the rate of change of the number of bats, where time t equals 8. I think we're good. We've done everything they asked us to do.